Okay, welcome. This is my exam presentation. So hello, and let me start. Okay, my name is Jose Islas Delfin. You know that. uh, Here you will find my link for my video. This video. First of all, let me start with the problem one, Newton's law of cooling, where they give us the Newton's law of cooling. Here it is. And with what is asked from us is to derivate this in order to get a function of time, of temperature and time over time, you know? Okay. Well, first of all, and they give us they give us like a situation for aluminum, but the first step in this is to is to derivate the formula. So what we have to do is rearrange it so that we get time on it on the other side, to make the function. So yeah, you the first step is to move this to this side, this dt, and move this to the other side, right? Okay, now we're ready to derivate. So yeah, that's pretty simple. Like this is k is the constant, and also, well, you know that 1 over x, the derivative, the integration the integration of the 1 over x is like normal logarithm of x. So we have normal logarithm of t minus ta plus the constant, and the integral of dt is just t. That's simple. So yeah, we obtain this part. What we want to do is like to make life simple for us, So we just make the constants a single one. So we make this constant a and constant b, like we pass this and rest them, so we have just one constant. I will I will make it faster because I take it too much time and I don't want to repeat this video. Yeah. So what we get is E over ln of this, and we have EC because we have, so in to get rid of the normal logarithm, we use this identity. So we have to do it for all of it, and we get this. We just know that e to the c is also a constant, so we might as well call it also a constant. So yeah, we want to know the value of that constant, so we make it time equal to 0. Time equal to 0 cancels, makes this equal to 1, so we get that c is equal to this relation of t minus ta. And yeah, that's pretty much it. We get the value for c, and we plug in the value, right? So we know that e minus, to this is multiplied by c with each this part. And what we do to just make it a function of temperature, we pass this to the other side, so passes like a sum, and we just get normal temperature as a function of time in this part. And we have the values that were given to us in the instruction, right? So we have normal temperature here and ambient temperature here. So what we know is that it starts at 25 degrees Celsius, and it will go up because of this was an oven, right? Yeah, this was an oven. So yeah, the thing is trying to mm, is is obtaining energy from the oven, right? So yeah, yeah. So we get also what we're looking for in here is actually the value for k, the constant, um, because we don't know it, right? So we plug the values that we know, and we just solve for k. Well, that's pretty much this, I think. To whoever who is watching this, I please enter to the document. I did a lot of effort. I make a lot of effort to make it like actually able to understand. I didn't make it in a notebook, so the one who checks my exam actually is easy for them to understand. So yeah. Um yeah, so we solve for k. This is the value of k we obtain, and we plug in the value, and this is the final formula we obtain. And the problem also says that after the thing is like heated, it's taken out of the oven to a lower temperature, so now it's cooling, right? So yeah, we now have another values, and we now have to obtain for the value of time to know at which time it's going to reach the temperature of 26 degrees. So now we solve for time, which is pretty much the same we did on the last part, right? So yeah, we did all this, and we obtained that well, this time of seconds, which I I think it was like 50 minutes, more or less. And now we have to make it on MATLAB, the code for MATLAB, both for the heated and the cool part. So yeah, I'm going to go to MATLAB, open my math program. I don't know what's happening. Yeah, so my computer is pretty much old. Oh, I think you can see it right now. So yeah, yeah. After that random fact about me, now you can see this is my code. We set the parameters like the data that we know from the exercise, or that we obtain from the calculus. Um, Also, we need to make this easy for MATLAB to understand. So we need to make things like the point at which it will start, like the time vector, and for the start at 0 and up, up until the final time, the final temperature, and make the step size. Also, we set the formula. Um, and now we use the Euler's method for heating, right? So yeah, so this is pretty much like plotting the things on well, stating some parameters for the graph later. And this is the part of the cooling. So we have like the other formula that we made, and this is pretty much the plot scene. We set we make the names for all of the things on the yeah. So what we can see is that this is the part of the cooling because it starts at 250 something degrees, which was after we took the thing from the oven, and it's cooling down, which is this. And this is the part of the heating, right, which is the only other thing, right? So, well, it ascends, and it reached the temperature at which we later took the thing out and start cooling, right? So yeah, I'm going to go back to my things because I'm okay. we have an electric heater and we have this thing. The main thing we have on this formula, which is the heat transfer equation, is that it doesn't have time. So we have to integrate. Uh, well, first of all, we need to integrate time to the formula, and after that, we have to integrate, right? So what we have to do is that, well, also the problem is pretty nice because it gives us this fact that the thing we are using to heat is burning at a pace of 1,000 watts, and we know that watts is joules per second, right? So now with that we have that relation, we plug in the time variable, right? So yeah, we know that um, the power, which was the watts, the 1,000 watts, is equal to the heat transfer or heat absorbed over the time, which I already said is joules per second. So we have that. And with that, we know this relation. So we know that dq is equal to the power over time, right? That power is heat over time, right? Well, the heat absorbed over time. So yeah, we pretty much have now this relation. We need to like fusion both relations. So we know that we plug in the q over time, and we also make time an aspect from this part of the formula. So yeah, now we pretty much have it simple to integrate. So yeah, well, to make it like easy to integrate, I also plug in the numbers so that I always remember which are the constants. So yeah, I plug in the power, I plug in the mass, the C constant, the heat constant, and I just leave the variables by themselves, which is temperature and time, right? So yeah, we just simply integrate because this is actually pretty simple. So the integration of dt is, well, it's just this, so we pretty much have this, and we have this constant, so we take it out, which is this number right here, and the integration of this is just time. Because this is an integral, we have the plus c, right? But what is plus c? We know that plus c is just the temperature at which the seawater is at the very start of the time. So we just know because yeah. So we just make it c equal well, it's not equal, it is the fact that it is initial temperature. So we know that. So now we pretty much have our formula, right? So yeah. And now we have to again use MATLAB. So I'm gonna start MATLAB again. I hope that it doesn't crash out because the other time it exploded. Um, so yeah, we have our graph, right? Well, this is pretty much the same as the last exercise. We set up our values, we plug in our formula, and and yeah, we just plot our graph. So imagine this is the start of the initial value for temperature, and this is like the slope of how temperature of the seawater will increase over time, right? With the help of the heat, right? So yeah, I'm gonna pass to the part of the matrices and the curve fitting. So yeah, I for this exam it was nice to have it at home because I could like investigate some things that helped me do this part. We have these things that help me like create like the multi how do I say it, coefficient multi coefficient formula that will help me like create values that could stick close or like represent the they name it as noise. I don't know why, but they make it like as noise, which is like values really close to our actual slope. So yeah, this is pretty much the same. Well, no, it's not the same, nothing like the same, but you understand, like you obtain similar values that represent a more error-wise slope, you know? Um, so yeah, you can check it out because I make it a really attractive PDF. Yeah, we have this problem of thermal equilibrium. Um, so yeah, with thermal equilibrium, we have both two things. We have a water and a part of copper. This was pretty much straightforward with the things we have to do. So yeah, we need to understand that this is a closed system, first of all, to know that we can apply the first um, thermodyn thermodynamic law, which is that the well that the change in internal energy of a system will always be equal to the heat transfer of the systems minus the work. So yeah, our system doesn't really have any work. So yeah, we just have that the relation that the change in internal energy is equal to the heat transfer. So from this we know that that there is no any plus energy on the or less energy, in the system when from the point it starts to the point it finishes. So we know that the energy or the heat that the that a thing lost is equal to the energy that the other thing gained. So we just need to find those. We can find those values by that relation, right? Because at the end, from this we know that the temperature that the hotter thing loses is equal to the same that the heat the cool thing gained, right? So yeah, we just said that the well, first we have to state our formulas. When we have two materials here, we have copper and we have water. We state our values. We have the things that it said on the document, and also we need to check for the specific heat, which we could find on the documents on the that the professors gave us on Canvas, right? Here is the link if you don't believe me. So yeah. We set our formulas. First, the copper kernel, which is this. Uh, and we know that the water is this. And also, we know that the TF in here is equal to the TF in here. Why? Because when both things enter in contact, they want to finish at a thermal equilibrium, right? So they pretty much they will finish the same at the same temperature, even though they they are pretty much temperature difference at the start, you know. Um, so yeah, we just have to, since we know that this is Q for water and this is Q for Carol. So we know that this is equal to this. So we need to find, we just state that relation and solve for TF. So yeah, we do a lot of mathematics, we do a lot of calculus, and we finish that the TF for both things is 48.2 degrees. Yeah. Finally, problem number 4. Determine expansion of a solid cone. So yeah, a solid object. Uh, ah, the first thing that the problem wants us to do is to prove why this formula right here transforms on this formula right here. So yeah, we need to prove things. We need to prove formulas, right? So yeah, we know. Well, what I did is state a really simple example. So yeah, how do I prove that linear expansion is correlated to the volumetric expansion? Well, the volume expansion of an object, right? So yeah, first let me state a simple fact. We know that L, which is the length of something after a linear expansion, will end up as the length plus the difference in length after the thermal expansion, right? And also, we know for a fact from our elementary school that the volume for a cube is 3 times L, right? So that's pretty simple to understand, I think. So yeah, we can now state some facts because, so we want to know the volume for this, then the volume for this, which is, we know that the volume for this is 3 times L, so why not would it be the same for this? So we know that the length of one of the sides is this thing, L plus delta L. So we pretty much have to use 3 times that to know the volume for that, right? And we also know that that this thing, the delta L, is equal to this. From what? From the thermal expansion law. So this is another fact that you can you can check. Um, and you can't deny. So yeah. We have delta L is this. So we can just plug in the values. Pretty simple, right? So we plug in this in here in the delta L. Now we have this formula right here. Yeah. Um, and we have this tree alone right outside. So let's let's put it with his friends, right? So we have 3L plus 3 times this thing, right? So now we have this another formula right here, but we know something. We know that 3 times L is equal to the initial volume. So yeah, to the volume before expansion, right? So we can also put 3L as the initial volume and also and also pass it to the other part of where is another volume. So we know that the new volume of this thing, we can rest the initial volume. So we have the fact that to make it a simple formula, we state this as delta volume. And delta volume will be equal to 3 times this thing right here, to the linear expansion thing. So they also ask us to plug in this thing right here. We also have this fact. So why not just make it simple for us and multiply it and state this law? And also, again, we know that 3 times L is equal to the initial volume of the thing. So we can also put this thing right here. And the delta in temperature, well, is the same as it would be in the linear expansion. So we just state it at, as that constant, that because it wouldn't change. If you make it linear or volumetric, is the same delta L, so we don't have to change it. So yeah, we get some values to know how much the volume of a thing would be after expansion. So yeah, we just calculate it and we get this. Also notice that the amount it like actually expanded is pretty much only this part. So someone could say that the volume increase after expansion isn't pretty big. Is something like to look at or something distinctively from the topic. And finally, we get to the problem number 5. We get this diagram of a gas that is expanding. How we know that it's expanding? Because of this arrow right here. Because this arrow is pointing to here, and here the volume is bigger and the pressure is bigger. So yeah, it's expanding with just from this arrow. So yeah, let's analyze a bit more. Like I said, we know that the gas is expanding because volume passes from a minor value to a bigger value, and also the pressure. So yeah, it's expanding. Also, we just we would we can integrate a bit of chemistry to our lives. It wouldn't be bad. So we can remember this formula, which is Pancho Villa no regresó a Torreón. A little joke from my chemistry teacher that I always remember. But yeah, we know we have this relation, right? So that pressure times volume equals to the moles on the gas times the R gas constant times the temperature, right? But we want to know what if the temperature would increase or decrease from A to B. But how do we know that if we don't have got any values? Well, if we just like use our eyes, I don't in a fun way, not in any kind of rude way. Um, we know that these two are constants, right? So they doesn't change no matter the increase or decrease of the other values. But these others can increase or can decrease. So we get a relation from that. We get that as much as this and this increase, this will also increase. If this and this decrease, then this will decrease. Why? Because a lower number by a lower number is equal to a lower number. But if you increase those numbers, then the number will be equal to a higher number, right? A bit of logic. So yeah, we know for a fact that it will expand no matter what, because the numbers here of VB and VV are bigger from BA and PA, right? So yeah, we know that it expands, right? Finally, we want to know the work that the gas is actually making, right? And now they give us values, so so we can break down the problem. I know we can use integrals to know the area under the curve or the slope or whatever you want to call it. Uh, whatever the name is, right? Yeah. So we can break down like the form. We know that this is a triangle and this is a rectangle. Yeah. Um, and we use these values like to find the total length and the total like altitude. So we want to know the area of these things. And we get that PV is equal to this value right here, 0.11 meters squared. And we get this thing right here, which is VA, 0.07 meters squared. No meters squared, meters cube. Please forgive me. So yeah, we know the value here and the value here, but we want to know the value of here, right? So we just rest. Pretty simple, right? So we know that between here and here are 0.04 meters cube. And we know that the altitude, which is PA, is equal to zero to, like uh, 1 to the 10 to the power of 5 pascals. So we know that the area that this represents is equal to 4,000 joules. And now we're missing the triangle. Yeah. So we find the area of the triangle. Pretty nice. The using, like elementary school that facts to solve my college exam. So yeah, we know that the altitude of PV is this 1.4 10 to the 5 pascals. And we know this, so we just rest to know the distance between PA and PV, right? So we get that it is 0.4 to 10 to the power of 5 pascals. And we already did this area, which is VA to VV. So we just got to multiply and divide it by 2, which is something I just noticed I didn't did, right? Yeah, I will correct that on the document. So please um consider it consider it done and check the document. Thank you for your attention. And well, thank you. This has been a really good exam, and thank you, teachers. I have returned from the dead, and I didn't live never. So yeah, like I said, you need to to find the area of this triangle, which is this times this divided by 2, obviously. We get 800 joules. We just sum it like simply, and we get 4,800 joules, which I always knew. Yeah. So thank you again. And now, thank you for everything. Bye.